Hello and welcome to this episode of Physical Attraction. Today we're going to be dealing with one of the most important and one of the most philosophically, beautifully depressing aspects of physics. The second law of thermodynamics. We'll get into the knotty and fascinating discussion of entropy and what it means to say that the world is always becoming more disordered. Because it turns out that in life and in physics, you can't win. You can't break even. To understand the second law, you need to know about entropy. Entropy is a complicated concept, so you'll see that it's defined in lots of different ways. You can think of it as a measurement of how disordered a system is. You can also think of it in terms of the quality of the energy that you have. Some energy can be used to do work. It's organised energy, like the energy of a driving force pushing in one direction. Some energy can't be used to do work. It's disorganised, random fluctuations of molecules of gas in a jar, for example. These are the ideas to have in mind the whole time. Entropy as a measure of disorder, and as a measure of how useful energy is. Work is high-grade energy, and heat is generally low-grade energy. And as we'll understand, every process of converting energy into useful work involves some losses of heat, and that has profound consequences for human activity and our understanding of the universe in general. But scientists didn't just go from nothing to a definition of entropy. So to really understand, we have to go back into history to see how the first law and the second law first came about. Sadi Carnot was an interesting man. He was a French engineer and mathematician, and his father had been part of the Directory that had taken over France after the French Revolution in the 1790s. He was investigating engines, mathematical models of engines. Now we should define this. An engine is basically a process that turns heat into work. So the engine in your car is converting the heat that's generated when you burn the petrol into work against friction, organised motion in the direction that you're driving the car. The efficiency of an engine is what fraction of heat can be converted into work. So an engine with an efficiency of 1 or 100% means that you can convert all of the heat into useful work. Some engines had already been designed by then, but they were very inefficient. You needed to put in a lot of heat energy to get a very small amount of work, and people were constantly looking for new improvements in their efficiency, so that you needed less fuel. Their ideas were usually along the lines of, what if we use something different in our engine? Most engines use steam to work, but maybe they thought there was a substance that was better at converting heat into work. Engines require the flow of heat. So generally there are two parts of the engine. There's a source of heat energy at some hot temperature, T source, and a sink of energy at some cold temperature, T sink. What Carnot showed, purely mathematically, purely theoretically, from the conservation of energy, was something amazing. It didn't matter what substance you used in the engine. There would always be a maximum theoretically possible efficiency. And it was the following. Efficiency is 1 minus T sink over T source. That's 1 minus the temperature of the cold sink divided by the temperature of the hot source. So you can see from this formula a couple of consequences. You can never have an engine with an efficiency of 1 that perfectly converts heat into work. It will always be less than 1. To get a perfect engine, you'd need T sink over T source to be 0. Remember, we're using the absolute scale of temperature here, so 0 degrees is the coldest anything could possibly get. But that would either need the cold sink to be at absolute 0 temperature, which is impossible, or the source of heat to be at infinite temperature, which is also impossible. This means that when the second law says you can't break even, it means that in every possible process, there are heat losses, energy losses, that dissipate throughout the universe. That energy is gone forever, it's disordered, it's lost. There's no way to recapture it. You'll always lose something. You can't break even. And it turns out that his abstractions that apply to heat engines can actually be generalised to every process that we know of in the world. And in reality, the situation is even worse. This efficiency, 1 minus T sink over T source, is called the Carnot efficiency. And there are usually other processes that stop you from even getting there. Alongside this, it's super difficult to get the temperatures to be very different in practice. Imagine the difference between a steam and ice being your source and sink. So for a car engine, you'd need to have steam in one part of it and a block of ice in it somehow in the other way, And then you have a T-sink of 273 and a T-source of 373. That's in Kelvin, so 0 and 100 degrees in Celsius. You might think that ice and steam are very different in temperature, and getting towards the theoretical limit of what we can actually keep substances at, but that only gives you a Carnot maximally efficient efficiency of about 27%. In reality, we can use superheated steam to get a better temperature difference, but the real-world efficiency of thermodynamic processes is rarely more than 30 to 40%. And this theoretical result has huge consequences. In all of our fossil fuel and nuclear power plants, where we convert heat into work, most of the heat that's generated is by burning the fuels. Well, it's all lost. It's not that we build inefficient machines, it's that the laws of physics, and specifically the second law of thermodynamics, prevent us from realistically making them any better than this. Now, we've had these kind of power plants for decades, or more than a century, and yet they're still at these efficiencies of 30 to 40%. If it were easy just to boost the efficiency by 10%, well, of course, power plants would stand to earn billions upon billions from that, given the amount of fuel that they burn. But they can't. The laws of thermodynamics prevent them. The ideal engine, then, is called a Carnot engine, which leads us seamlessly onto this episode's physics-based chatterlines. Are you a Carnot cycle because you're as close to perfect as it's possible to be? Or if you're feeling cynical and jaded, are you a Carnot cycle because you're ruthlessly efficient but technically unattainable? So this might seem all a little bit specific and abstract. Maybe it even sounds a little bit like engineering and not physics. But heat engines are just how Carnot thought of this version of the second law. What he's touched upon doesn't apply just to heat engines. He'd stumbled upon a fundamental law of physics that affects any flow of energy, from the molecules in our bodies to the shining stars. Unfortunately for Sadi Carnot, the brilliance of his discovery wasn't appreciated for quite a long time. It just seemed like a lot of theoretical rubbish about heat engines, and perhaps the engineers were still convinced they could beat the laws of physics. Or maybe the physicists weren't willing to appreciate the genius of an engineer. It took until later in the 19th century for physicists to pick up where Carnot had left off. First, Rudolf Clausius made a statement that might seem pretty obvious. He pointed out that heat flows from hot objects to cold objects. And of course we know this from our day-to-day lives. But he noted that the only way to get heat to flow from cold objects to hot objects, so the cold one gets colder and the hot one heats up, is by doing work. You have to force the heat along, and there has to be some change somewhere else in the system. You can think of temperature like a hill. It's a pretty good way of thinking about it. Heat naturally flows downhill from hot temperatures to cold ones. If you want to push heat uphill from cold to hot, you need to do some work. Then Lord Kelvin came along, and what he realised was, in a way, completely related to what Carnot had figured out decades before. He said that it's impossible to have a cyclical, that is, a repeatable, a cycle process, that completely converts heat into work. In other words, there always has to be a flow of heat from hot to cold. You can convert some of the heat into work, but there always has to be some remaining as heat that goes from hot to cold. So you can see that this is really similar to the Carnot efficiency argument. You can't have a perfectly efficient heat engine that turns all of your heat into work. By now, if you're unfamiliar with thermodynamics, your head is probably set to explode. We have 4 different versions of the second law. First, heat engines have this maximum Carnot efficiency that depends on the temperature difference. Second, heat flows from hot to cold, and you need to do work to push it uphill from cold to hot. Third, you can't completely convert heat into work. There always has to be some heat flow. And fourth is the idea you often see expressed: in an isolated system, entropy must always increase. All of these statements turn out to be the same thing, or parts of the same thing, the second law of thermodynamics. But seeing this is initially really difficult. I'll release a bonus episode explaining how the Kelvin and Clausius formulations are in fact the same thing. Last episode we talked about what is meant by a thermodynamic system, and for a system to be in a certain state. We said that a state is like an equilibrium for the system, so that nothing is changing with time. And you can characterise a state by saying this is the temperature, this is the pressure, this is the volume, etc. Actually, if you have knowledge of the substance that you're dealing with, you can figure out one of these from the others using the equation of state. The most famous one is the ideal gas law, which says PV equals nRT. That means the pressure multiplied by the volume is equal to the amount of stuff you have multiplied by the temperature. This might seem complicated to remember, but it's actually not too bad when you think about what you'd intuitively, physically expect to happen. If you increase the pressure while the volume stays the same, the temperature has to go up, because PV has gone up, so nRT must go up as well. Similarly, increase the temperature at constant pressure, and the gas will expand, and so on. This equation is incredibly useful for predicting how thermodynamic systems behave, and it encodes a lot of our expectations as to how gases will act when you heat them up or make them bigger and so on. And it means that you only need to measure a few quantities and you can work out the last one. But this is what's called a macro state. Macro means big on a large scale. There are also microstates for a system. To understand this, it's best to go back to our favourite example, atoms of gas in a jar. The macro state is, okay, how many atoms are there, what's the temperature, the volume, the pressure of the whole system? The micro state is, okay, what are the positions and speeds of every atom in the gas jar? So you can see that there are billions of possible microstates, an uncountable number of possible microstates, because each atom of gas could be in all kinds of positions and have all kinds of speeds. But actually, many individual microstates will correspond to a single macrostate. You can have lots of configurations, lots of positions and velocities for the atoms that will still give you the same temperature, pressure, volume when you measure these properties for the whole gas. So individual macrostates of temperature, pressure, etc. have many microstates associated with them. Each microstate has a certain probability, a certain likeliness to happen. And this too kind of makes sense when you think about it. It's really unlikely that all of the molecules will crash into one molecule at once, making it super hot, or crash into one wall of the jar at once, so there's no pressure on the others. It is possible to imagine a distribution of the particles where all of them are completely still except for one that's moving with all the energy of the whole system, but it's extremely unlikely that this would actually happen in physics. So, in fact, what you have is the microstates where all the molecules have a fairly similar energy, according to a normal thermodynamic distribution, and they whiz around happily. They're far more likely to occur, these microstates. They have a higher probability. So where is this going? Well, in some sense, you can describe the entropy of a macrostate for the system as the number of microstates that the macrostate has. If there are billions of ways of distributing energy among the molecules that give you the same temperature, pressure, and so on, that's a very high entropy state. If there are only a few ways you can distribute these things, then the state is low in entropy. So entropy is a measure of how many different microstates correspond to your macrostate. If there are 15 billion ways of having a sort of flat system where everything looks similar, then that's high in entropy. But if there's only one way of having a system where all of the molecules are ordered and march together, then that's a very low entropy state. And now you can begin to understand what we mean by saying that entropy is like a measure of how disordered a system is. Imagine the atoms in the gas again. There are many microstates where they're all just whizzing around randomly with no particular order or reason to what they're doing. But there are fewer microstates where they're all moving in one direction, when you add some order to the system. Here's another way of thinking about it. Remember that whole fun story about an infinite number of monkeys bashing away at an infinite number of typewriters? If you give them long enough, then they'll presumably type everything that can possibly be typed, including the complete works of Shakespeare. In fact, this is exactly how we produce the scripts for these new episodes, which is why it takes so long to get new ones out. But we all know that if you actually tried this experiment for real, well, I guess Peter would be onto you and the monkeys would fling poop everywhere and things would fail. But we also know that the monkeys would produce a hell of a lot of gibberish, sheets and sheets of things that just didn't make sense, random letters and numbers, kind of like what you'd expect a monkey or the president to type. This makes sense. The complete works of Shakespeare, even the English language, or Hungarian for that matter, are very ordered systems. They have a lot of order, a lot of structure. And in all the possible states for a set of letters to be in, there's only one microstate that is the exact, complete works of Shakespeare. There's only one microstate that is 50 Shades of Grey, or the script to this episode. But there are billions of microstates that are disordered, jumbled nonsense. When we look at them, there might only be a few that we recognise as novels. The rest are basically indistinguishable macrostates, books filled with disordered junk. So you can begin to see this idea of there being many more disordered microstates than there are ordered microstates. We owe this idea of entropy to Boltzmann, a genius physicist, and it can be written in a simple equation. S equals K log W. So S here is the entropy. K is a constant that has the units of entropy. It's actually the Boltzmann constant that converts between temperature and energy, but you don't really need to worry about that. W is the number of microstates that we can have, the number of ways of arranging the molecules of a system to achieve the same total energy, the same state. So this will tell you what the entropy is, and because the log of a function, that is the function, the log of a function increases as it increases, so log x goes up as x goes up, although more slowly than x goes up. It basically says that the entropy increases when there are more microstates, W, that correspond to your macrostate. But this is a problem though, because we think that if you leave an isolated system alone for long enough and don't do anything to it, what it does is gradually explore all of its microstates. There's actually an interesting philosophical question about whether it does explore all of the microstates physically, whether it does actually, given long enough, manifest in all of them, or whether it just sort of explores the probabilities of all of these different things, but that's kind of by the by, I think. In the atoms of the gas jar, this is by collisions, heat and energy exchange that push you into new microstates. And eventually, inevitably, it will tend towards the ones that are high probability. It will tend towards one of the billions of microstates that are disordered. It will tend towards disorder and chaos. And, in an isolated system, entropy will always increase. And we can see processes we're familiar with as being manifestations of this increase of entropy. So let's say you inject some order into the gas jar, maybe by dispatching a fleet of molecules moving in one direction, or you give it some heat energy somewhere. The system will quickly explore the many microstates where those molecules are all jumbled up, moving in random directions, and the order will vanish, and entropy has increased again. And now maybe you can see how this is actually the same as some of the other statements of the second law. If we could convert heat, the disordered motion of atoms and molecules, into work which has order, which is useful, and which can go in one direction, then entropy would not have increased. In fact, if you can get heat, disordered motion of atoms, into work, ordered motion of atoms, then the entropy has gone down. And if we could get heat to flow from cold to hot, then we'd be reducing overall entropy. This one is a little bit harder to see, but the change in entropy is basically the flow of heat divided by the temperature. And so what it actually means is that if you have a really, really cold system and you make it even colder, the change in order in that system, it becomes much more ordered than the hot system, where you dump the heat, gets slightly more disordered. So hence the chat-up line, let's increase the sum of our entropies. It's cold outside. So let's explain this further. Imagine you have a really cold system and you supply a little bit of heat. Suddenly there might be 10 or 100 times more energy than there was before, and the molecules can occupy way more states than they could before. So that little bit of heat is worth much more to the cold system than it would be to a hot system. If you supply that little bit of heat to a hot system, it doesn't change things all that much. The system can occupy a few more states than before, but not so many. And that's why the change in entropy is heat divided by temperature. At lower temperatures, the same heat flow makes a bigger difference to entropy. Maybe another analogy goes like this. Imagine you start singing at the top of your lungs, Angels by Robbie Williams. Now I'm sure your singing voice is lovely, but this does make the world more chaotic. If you start singing Angels in the middle of a football match, it won't have much of an impact. Everyone's screaming and shouting already. It's already very chaotic. Your extra bit of chaos will not change things much. This is like heat flow at high temperatures. But consider an exam room where students are taking an important thermodynamics exam. Things are very ordered, very structured, entropy is low. If you start belting out karaoke classics in the middle of the exam, you will cause a lot of chaos. There will be a big change in entropy for your same small change in singing. This is like the flow of heat into a low temperature system. Both times, the amount of heat, your wonderful singing voice, is the same. But because one system started off disordered, high temperature, and the other was ordered, low temperature, the entropy is different. So dumping heat from a cold place into a hot place, somehow making the exam room quieter by pumping the noise into a football match, that's against the laws of nature. So now I hope you're understanding the second law of thermodynamics a little bit more. Entropy, which represents disorder and chaos, will always increase. This is a really fundamental mathematical physical idea. It seems very poetic, and it is very poetic. This idea that things always tend to decay, to disorder, to rack and ruin, that order and structure can't be reserved, that if you leave things alone, they're consumed by chaos eventually. But it's also a mathematical consequence of the laws of physics. This is reality, the world we live in. Arthur Eddington put it like this. He said in his book, The Nature of the Physical World, quote, "The law that entropy always increases holds, I think, the supreme position among the laws of nature. If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it's found to be contradicted by observation, well, these experimentalists do bungle things sometimes. But if your theory is found to be against the law of thermodynamics, then I can give you no hope. There is nothing for it but to collapse in deepest humiliation." You might try to think up counterexamples. Fridge freezers make things colder, right? They decrease entropy? Well, yes, but they also pump out heat at the back, more heat than they remove from the objects. Entropy in the universe as a whole always increases, because the universe as a whole is the isolated system that we need to consider. Say I tidy my room and arrange things neatly. I have, by my actions, in some way increased the order of the universe. By saying these words, I am in a sense producing order, structure, where before there was chaos. As you listen to this, hopefully neurons in your brain are firing in an ordered way. Connections are being made. Structure is arising. Entropy is actually decreasing, right? But this is because the things I've talked about are not isolated systems. We are effectively rearranging deck chairs on the Titanic, but the boat is still sinking. When I tidy my room, I generate heat doing it, and that heat energy makes the world around me slightly more disordered. I haven't done anything to decrease entropy in the world. I can never do that. I just rearranged it. I fought against entropy in my bit of it by creating some more somewhere else. As I type these words into my laptop, even the transfer and storage of information of any kind on a hard drive, whatever, is generating heat. This is why in the last episode we talked about the fact that futuristic civilizations might want to wait until the universe was much colder so that they could be more efficient. Because actually, they have to convert some energy into heat to store information. The mere process of information transfer, of calculation, of permanently rearranging atoms in a system, which is the only way you can store information, it creates heat that makes the universe more disordered. There is no physical way to store or process information without increasing the entropy of the world as a whole. Even in your brain, as the neurons fire, as you learn about entropy from me, your brain might have a little less disorder in it, I hope, as I explain. But in the universe as a whole, entropy always increases. And when this was discovered, it was philosophically troubling. Ludwig Boltzmann, the man who basically invented the field of statistical mechanics, which explains many things in terms of microstates and entropy changes, well, he was deeply disturbed by the second law of thermodynamics. Because entropy will always increase, and there's no way to stop it, it means that the evolution of the universe is progressing along one inevitable path. All forms of energy, eventually, find themselves turning into heat. All of that heat gradually dissipates across the universe. Things are gradually, but inexorably, becoming more and more chaotic. The stars will burn up and burn out. All of their heat will spread across the universe. We now know from cosmology that the universe will expand forever. As entropy increases, slowly, gradually, inevitably, all of the energy will turn into heat and spread across the universe, as things unravel and tend towards the state of maximum disorder. In this world, the energy is spread thinly across an ever-expanding universe. In this heat-death state, nothing can exist but a dull, cold soup of particles and photons. There are billions upon billions of microstates available, but they're all highly disordered with no structure in them. There can be no life. There can be no thought. This is the ultimate fate of everything. Entropy maximized. Nothing we can do will stop it. In fact, everything we try makes it worse. Regardless of how beautiful or sturdy a palace we build, it will one day be dust and ashes. It was this realization, many say, that drove Boltzmann to suicide. From my perspective, though, the philosophical side of the second law of thermodynamics is just perfect. It's a perfect metaphor for humanity as a whole, the whole human endeavour. After all, we all know that we're going to die, and we all know that someday we'll be forgotten. No matter how famous you are, how much you manage to achieve, how many people adore you during your lifetime and afterwards, entropy will come get you in the end. We know that the seas will rise, that the sun will heat up and destroy our planet, and that all the information that proves we ever existed will one day be lost or unreadable. We can tidy our rooms, we can write words, we can build relationships with each other, we can build homes, and we can build cities. We can rearrange the world into something that looks orderly to us, for a while. We can keep it all together for a little while. But we know that this is only temporary, even if temporary seems to last a very long time. Entropy will always increase. Everything will always give way to chaos. We will die and be forgotten, and the order that once was will be lost, and eventually the whole universe will be a dull thermal equilibrium soup. But in the meantime, there is still change. There is still flux. There are still flows. From the floods of heat and light in our lamps that light up the city skyline, to the flow of vibrating molecules that allow you to hear the words I'm saying now, to the rush of chemicals in your brain when you feel joy or fear or sorrow. These flows take place always governed by the second law. Entropy and disorder are always increasing, but in the meantime they can still be beautiful. We know it's pointless, we know that in a sense it's practically meaningless, but we keep going. Every morning we get up and do the things we feel we have to do. We go through the world and we rearrange its chaos in a way that pleases us slightly more when we can, even if we are just rearranging deck chairs on the Titanic. We do every stupid thing that keeps us alive and every stupid thing that makes us feel alive. It won't save us, we can't win, we can't break even, we can't even get out of the game, but we keep going. Maybe we don't know anything else, maybe we're foolish, maybe we just like to spit in the eye of inevitability. Maybe our purpose is just this, to fruitlessly, hopelessly struggle against the slow unravelling of everything. Maybe this is what it means to be human. For a little while, we can fight the tide, we can resist disorder, we can bend the world to our will, we can stop everything from falling apart in our own little ways. For a little while, we can look at the chaos around us and tell ourselves stories about what it might mean. We are engines. We turn the heat, we turn the random twistings and turnings of the universe into narrative, into order. We can't break the second law, but we can feel like lawbreakers. We can kid ourselves, for a little while, maybe a long while, maybe as long as it matters. We can kid ourselves that the game can be won. Thanks for listening. If you've enjoyed this episode and the rather lengthy philosophical rant at the end of it, you know there's all kinds of things you can do to support us. One of the ones that would really be nice is going on to www.physicspodcast.com. You can donate to the show, you can leave us reviews and comments, anything, any topic you want me to talk about, that kind of thing. It's all good. You can send it there. You can follow us on Twitter at PhysicsPod if you're into that. There's a Facebook page, Physical Attraction, where you can also engage with the shows. You know, I read all of this stuff, so if you have anything you want to say about the show, or suggestions for improvement, new topics, people to interview, I'm here and I'm listening. Until then, in your own little ways, keep fighting the fight against entropy. I know it won't work. I'm here with you too, fighting as well, until the end of our days.